Hey there, students. So in the last video, we were talking about solving for K given equilibrium concentration. So it was already telling us how much of each reactant and product was at equilibrium so that we could solve for K. But there's a different way that we can use these equilibrium expressions, and that's for us to figure out how much stuff is present at equilibrium and how much stuff we started with in some cases. So we're going to be following a series of steps in order to solve for these kinds of problems. So it's really important that you all read the questions carefully to determine whether or not we are already at an equilibrium mixture and it's giving us the concentrations at equilibrium, or if it's telling us how much of each reactant we're actually starting with, an initial concentration, because we're going to tackle those two problems very differently. So in these kinds of problems, we're going to be setting up what's called a Rice table. So when we're solving these kinds of problems, we want to first write our balanced chemical equation. That should be our number one important step in any kind of chemistry problem, having a balanced reaction. Then it's going to be important to write your equilibrium expression, and I talked about this in the last video. It's important that you write your expression without any numbers in there at first, so you can make sure that you're writing the correct expression and you're raising each expression to the correct power. We're going to set up a Rice table. This is going to include our initial concentrations and how factors are going to change during equilibrium. Once we get our Rice table filled out, then we're going to plug that back into our equilibrium expression so that we can solve for X. Now, the problem with some of these problems is that sometimes our X in our problem is going to be negligible and sometimes it's not. So these first three bullet points in black, those are talking about the correct way that we can make X negligible. It's this, 5% difference, or if it's less than 5%, the value of our equilibrium constant. But we don't look at that. We're going to make it really, really, really simple. So I want you to look at this note in red. We're going to use this rule down here. If the numerator and the denominator are both at the same power, so if they're both squared or if they're both cubed, then we're going to keep the X. But if they are at different powers, so if the numerator is at second power and the denominator is first power, or if it's at third power, then the X in the denominator only is negligible. So we always keep the X in the numerator, but if they are at different powers, the numerator and the denominator, the X on the bottom is going to be negligible, which means we're just going to cross it out. So we'll do some problems where I can show you how this is going to look. So here, it gives us a reaction, and I don't know why it does this, the box instead of the arrow. So it says carbon monoxide reacts with water to form carbon dioxide and hydrogen gas. The equilibrium constant for this reaction is 5.0, so that's our K. Consider an experiment in which 1 mole of carbon monoxide and 1 mole of water are mixed together in a 1 liter flask at 700 Kelvin. Calculate the concentrations of all species at equilibrium. So what I want to point out here is that that 1 mole of carbon monoxide and that 1 mole of water are your initial amount of moles. This is not telling us an equilibrium mixture, so that's why this problem is going to be different from the ones from the last video. So we're going to have to set up a Rice table. Now we see over here it says reaction, initial, change, and equilibrium. So I'll tell you guys how that is going to work as we go through these. So we're going to write our reaction up here. CO plus H2O is going to yield carbon dioxide and hydrogen gas. Okay, so it gives us our initial concentration. Now, if it gives you moles and volume, make sure that you are dividing your moles by your volume to get your molarity. So we have 1.0 molar solution of this. No, it's not a solution because it's a gas. And 1 moles of that. Now, your products, we start with 0 of because we don't have any products initially. Okay? Now, the C is going to represent the change. So how are those concentrations changing? Well, we know that our reactants are going to decrease So we're going to have a minus X here for our reactants. And we add products as the reaction takes place. So we're going to have a plus X over here. Now, if we had coefficients, we would be putting those coefficients in front of the X. And we'll see that in one of those later examples. So our equilibrium row, that's where we put our initial and our change together. So we're going to have 1.00 minus X, 1.00 minus X, and then X and X over here. Now, before we do any kind of calculation, we're going to write our equilibrium expression. So our equilibrium expression is going to equal the concentration of the carbon dioxide times the concentration of the hydrogen over the concentration of the carbon monoxide and water. Remember, only gases and aqueous solutions are going to go into our equilibrium expression. So now that we have our equilibrium expression, we can go ahead and plug our values in. So our K was given to us in our problem, so it's 5.10. And our values for our products are X and X. And then we're plugging in our equilibrium row here because this is our equilibrium expression. So then on the bottom, we're going to have 1 minus X and 1 minus X. So I just want to show you guys a different way of writing this. So what we really have is 5.10. We've really got X times X, so that's X squared on the top. And then we really have 1 minus X squared on the bottom because it's 1 minus X times 1 minus X. So I write it this way to show you that the power in the numerator is the same as the power in the denominator. They're both raised to the second power. So that means we have to keep our X. So what we're going to do first is take the square root so we don't have to mess with the 1 minus X times 1 minus X situation. So we're going to take the square root of both sides here. That means, let me take the square root of 5.1 here. So that's 2.26. Yes, 2.26 is going to equal X over 1 minus X. So then I'm going to multiply both sides by the denominator to get the X out of the bottom. So I'm going to go, let me just draw an arrow up here. So I'm going to have 2.26, oops, 0.26 minus 2.26x equals X. Okay, so I've got to distribute this 2.26 to everything that's in the denominator. So now I've got to get my X's on the same side of the reaction and make it positive. So I'm going to have 2.26 is equal to 3.26x. Because right now there's a 1 in front of the X on the right. So now I can divide both sides by 3.26. And that would be 0.693. Now, this is not the answer because it's asking for the concentrations of all species at equilibrium. So then what we want to do is we want to plug our X value into our equilibrium row to get the concentrations of each substance at equilibrium. So we can see that carbon monoxide is going to equal water because they're both 1 minus X. So I'm just going to do 1 minus X over here. And the concentrations of the carbon monoxide and the water are both going to be 0.307. And then I see that my carbon dioxide and my water, oops, are going to equal each other. Sorry, hydrogen. I keep saying that today. And that's just going to be X. So this is going to be 0.693. And this would be my answer here, where I have the concentrations of each substance at equilibrium. Okay? So let's look at this next question. Calculate the number of moles of chlorine produced at equilibrium in a 10-liter vessel when 1 mole of PCl5 is heated to 250 degrees. Now, again, the temperature isn't important to our calculations. It's just because the K value can change at different temperatures. That's why we specify it in the problem, but it's not affecting our mathematical calculation at all. So first off, this should be a double arrow here instead of this funky little box. Let me just change this. Now it tells us our K value, 0.0041, and it does not give us equilibrium mixture concentrations. It's giving us how much initially we started with. So first off, we're going to have to find our initial concentration of the PCl5 because we have 1 mole in 10 liters. So we have to do moles divided by liters to get our concentration. So our initial concentration is going to be 0.1. Okay, and again, we always start with 0 products. So we start with 0 products. So our change, we're going to lose some reactants and we're going to gain some products. So that's why it's plus X over here on this side. And then our equilibrium row, we add those 2 rows together. So we would have 0.100 minus X, and this would be X, and this would be X. So before we start plugging any numbers in, we're going to write our equilibrium expression. So equilibrium is going to equal PCl3 times Cl2 over the concentration of PCl5. So once we get that, we can go ahead and start plugging some things in. Our K value is 0.0041. Because we have PCl3 and Cl2 on the top, our top is going to be X times X, or X squared. And on the bottom, we have PCl5, so that's going to be 0.1 minus X. And there's no power here. So remember I said, if the numerator and the denominator are not at the same power, then the denominator X is negligible. So we can see that these are not to the same power. The numerator is to the second power. The denominator is to the first. So that means we're going to make X negligible. So we can just kind of get rid of that and pretend it's not there. So we're going to go ahead and multiply both sides by the denominator. So we would get, let me change my color again, 0.00041 when we multiply by 0.1 is equal to X squared. So we want to take the square root of that, and we would get 0.0202. And, oh, I forgot. Hang on a second, I want to take the square root of this. So this, I shouldn't have put the X squared there. There we go. I was just confusing myself. So X is going to equal 0.020. And again, this isn't my answer because I want to go ahead and plug this back into my equilibrium row so that I can find the number of moles of Cl2 at equilibrium. Well, Cl2 is equal to X, but this is molarity. And don't forget, I have 10 liters. So to find my moles, I need to multiply this by 10 liters. Because molarity is equal to moles divided by liters. And so I would get 0.20 moles. Okay, so that would be my answer. Whoopsie. Okay, let's take a look at this next question here. So it says, if the K for the following reaction is 2.4 times 10 to the negative 9, and the initial concentration of CO2 is 2 molar, what are the concentrations of the substances at equilibrium? So we can see here that we have our reaction already written. Carbon plus carbon dioxide yields to carbon monoxide. So I'm going to go ahead and put my initial concentrations. Now, first off, I noticed that carbon is a solid, and solids do not show up in equilibrium expressions. So this whole section right here doesn't apply for this equation and this problem. So we just focus on gases and aqueous solutions. So the initial concentration of carbon dioxide was 2.00 molar. And we always start with how much product? 0 product. So now I want to go ahead and write the change. Well, I can see that my reactant is going to go down and my product is going to increase. But see how we have this coefficient here in front of the carbon monoxide. We put that coefficient in front of the x. So this is plus 2x. So when we write our equilibrium row, we have 2.00 minus x, and then this is 2x over here. Okay, so I write my equilibrium expression first before I plug in any numbers. I've got carbon monoxide, and don't forget to square it because of that coefficient again. And then I've got carbon dioxide on the bottom. And I can go ahead and start plugging in my numbers. So I have 2.4 times 10 to the negative 9, very small value of K, favoring the reactants. And then I'm going to have 2x squared on the top, and I'm going to have 2.00 minus x on the bottom. So remember, if these are raised to the different powers, then the x on the bottom is negligible, and I can go ahead and just make sure I don't include that in my equilibrium calculations. So that means that I have 2.4 times 10 to the negative 9, and that equals 4x squared. I'm going to distribute that squared to everything in the parentheses over 2. So I'm going to take 2 times my 2.4 times 10 to the negative 9. And that's going to equal 4.8 times 10 to the negative 9 equals 4x squared. Now I'm going to divide both sides by 4 to get that 4 out from the x. I have 1.2 times 10 to the negative 9 equals x squared. Now to get x by itself now, I've got to take the square root of both sides. So I'm going to square root my answer here. And I see that x is equal to 3.5 times 10 to the negative 5. And that's going to be molar. So again, my answers, this is not my answer. It's asking for the concentrations of the substances at equilibrium. So once you solve for x, you plug it back into your equilibrium row. So my concentration of CO2 at equilibrium is going to be 2 minus x. So I do 2 minus x, oops, and I get 1.99996. So when I round to sig figs, that's actually just going to be 2. And then my carbon monoxide, I multiply my x by 2, and I find that my carbon monoxide's concentration is 6.9 times 10 to the negative 5. So this here is my answer because it gives me the concentrations of both substances at equilibrium. All right, so that's how you do equilibrium problems when you're given initial concentrations and not equilibrium concentrations. So as you're working on problems 9 through 16 on pages 7 through 8, if you have any questions about those, feel free to reach out and let me know so I can help you.